Assalamualaikum and a very good day. This is the last topic for our course, which is chapter 7, Chisquare test and ANOVA. Okay, by the end of this chapter, you should be able to use contingency table to find the expected frequency. We have introduced contingency table in chapter 2, and then if we have a contingency table, we will use chi-square distribution test to test whether from this contingency table we will have a two variable, and we want to test whether these two variable independent or dependent, whether these two variable have a relationship or no relationship between each other. Okay, next, you should be able to use one-way ANOVA technique to determine if there is significant difference among three or more means when sample size are equal or unequal. So let's say we have a three group of a same sample size. Okay, so each of the group will have its own means. So we are interested to see whether these three means have a significant difference or no difference at all. Okay. So for introductions, so in this section, we will cover about the contingency table. We will find the expected and observed frequency in order to test two variables for independence using chi-square independent test. Okay, before you start, let's recall quickly what is contingency table. Okay, simple example. Let's say we are in a pet shop. So in a pet shop, we are interested on the pet gender. Okay, pet gender. So let's say we are having pet cat, bird, dog. Okay, so the gender of the pet may female and male. So our variable is pet and gender. So let's say we have 20 female cat, 5 male cat. Okay, I just put any value. Okay, so this is all the total. This is 20 cat, 5 cat for male, 5 bird, female bird, 15 male bird, and then 10 female dog and 7 male dog. Okay, so this is a contingency table. So to test the variable, what is the variable? The variable is pet and gender. So we want to see, is there any relationship between gender and pet? So for this, we need to use chi-square independent test to see the relationship between these two variables. Okay, let's look at test two variable for independence, which is the chi-square test. So in general, if there are R categories of the row variable, okay, R category for row variables, C category for the column variable. So the contingency table is called R times C, which is row times column contingency table. So as our example previously, we have two R times C column. So we have 2 row and 3 column. Okay, which is now this contingency table is 2 times 3. So we are interested to find out whether the row variable is independent of the column variable by finding the expected frequency for each cell. Okay, so to understand the technique, we use the following formula to calculate the value of observation and also expected frequency. Okay, here O represent the observed frequency in cell ij. Okay, and then Eij is the expected frequency in cell ij. So I refer to level on the first classification method. J refer to level on the second classification method. So we have row variable and column variable. So each value in the cell is actually is the observed frequency. And this n refer to n I dot. Okay, this is referred to n dot j. Okay, so n1 meaning that the total for observed in the first row. So O11 plus O12, you get n1 1 dot. Okay, so O21, O22, you will get 2 dot, which is a total of O21 plus O22. And this one refer to n dot j. So you add the first column, you get n1, and you add the second column, so we will get N2. So the general rule for obtaining the expected frequency of any cell is given by the following formula. So let's say you are finding the expected value for this area, E11. So you are looking for N1 dot multiply with N dot 1, which is 1, right? So this one refer to n dot dot. N dot dot is the total value of this one plus this, you get the total. And it should be the same with this n1 dot 1 plus n dot 2. So you will get the same thing whether you plus these two value in terms of row or you plus this value in terms of row, you will get the same value. Okay, refer back chapter 2, what is contingency table. So the chi-square independent test is used to determine whether or not the occurrence of one variable affect to other. So as I mentioned before, then the test statistic for chi-square independent test is given by the following formula. Okay, so which is the summation Oj minus with Eij squared for each row and column, and then this one divided with expected Eij. So it is approximated by the chi-square distribution with the degree of freedom R minus 1 multiplied with C minus 1 degree of freedom. Okay, so to get the degree of freedom, so you must know what is your row and multiply with what is your column. Row minus 1 multiply with column minus 1. Where again O represent the observed frequency and E represent the expected frequency. The procedure for chi-square independent tests are as follows. So the first step, we need to state the hypothesis, H0 and H1. Step 2, compute the chi-square independent test statistic. Okay, so we find chi-square test statistic, and then next, the third step, you find the critical value for in the chi-square table. So we have chi-square table, and we will use this formula to compare with the compute chi-square independent test here. Okay, and then make a decision about the hypothesis. You reject the chi-square if the chi-square test more than what you read from the chi-square table, and then makes conclusion based on the decision. So what is your hypothesis statement? H0 and H1. So for hypothesis statement, H note, you need to know that the row and column variable are independent, not related to each other, which is X has no relationship with Y, where the H1 is the row and column variable are dependent or related to each other, or X has relationship with Y. Okay, for example, last time, so meaning that we can write as H note, let's say we have gender and pet before. Okay, so gender and pet are independent. That is our first statement for H note. Okay, and then our statement for alternative hypothesis, gender and pet are dependent. Okay, let's look at the first example. The manufacturing company wants to study the relationship of the presence of sodium carbonate towards the compression strength of sand composition. So the experimental data of the sample molding are shown in the following table. So this is the contingency table for these two variables. So this is the first variable, this is the second variable. So we want to see the relationship between these two variables. So at alpha equal to 0.01, can the company conclude that the presence of sodium carbonate is not related with the compression strength of the molding sand composition? Okay, so we want to study this. The first step, determine your H naught and H1. So your H naught is equal to sodium carbonate present is not related with the compression of strength of sand composition, or not related, meaning that is independent, where our claim will be at the H naught. Okay, and then the alternative hypothesis, sodium carbonate present is related with the compression strength of sand composition, which is this one refer to sodium carbonate present is dependent to compression strength of sand composition. Okay. So this is your observed value for with sodium and strong 20, weak. This is the observed value. So whatever in the bracket is the expected value. So how to get the expected value? For example, we want to know the expected value here, E11. Okay. So E11 is N1 N1 dot multiply with Nj dot. So 1 total of 20 plus 40, you get 60. So N1 dot is 60. And then Nj dot is 30. And the total is 150. You see, 60 plus 90, you get 150. And 30 plus 120, also 150. So the first step, you need to find the total for each row and each column, and then find the expected value for E11, E12, okay, E21 and E22. Okay, so once you get all this, you can substitute in the formula of AIG minus EIG divided with EIJ. So you have E11, which is 20, minus the observed value minus with the expected value, divide with EIJ. Okay, so EIJ for this part is 12. Then the same thing here, the observed value minus with expected value, and then this is the divide with expected value. Observed value minus with expected value squared. Sorry, you need to square everything, divide with the expected value. Okay, this is the expected value for E11, E12, E21, E22. Okay, then if you get all this, so you just need to add all this value and you get the chi-square test equal to 11.111. So to find the chi-square critical, where you need to know your alpha, which is 0.01, and then your degree of freedom, which is R minus 1 times C minus 1. So your R equal to 2 and C also equal to 2. So 2 minus 1 multiply with 2 minus 1. So you know that your degree of freedom is equal to 1. With alpha 0.01 and degree of freedom 1, read from the chi-square distribution table, you will get 6.635. So this is your table 6 chi-square distribution table. So to get the reading before, so you know that your degree of freedom is equal to 1 and your alpha equal to 0.01. So the value that you get is from this table. So you must know what is your alpha value and what is your degree of freedom value to know the chi-square critical. So once you know your chi-square critical, you can compare with your chi-square test. Okay, so here you can conclude that since chi-square test, which is the value is 11.1111, more than the chi-square critical, which is 6.635. So what we can say that we reject H naught. Since we reject H naught, hence there is insufficient evidence to conclude that the presence of sodium carbonate is not related with the compression strength of molding sand composition. It is related to each other at alpha equal to 0.01. Now let's look at the next section, 7.2, Introduction to ANOVA. By the end of this topic, you should be able to describe the purpose of ANOVA, identify the assumptions that underlie the ANOVA technique, and apply the ANOVA hypothesis testing procedure. So the purpose of analysis of variance is to compare the difference of more than two population means. Okay, so we want to know the difference of more than two population mean. mu1, mu2, mu3, and so on. Okay, it is also known as factorial experiments. This approach allows us to use sample data to see if the value of more than two unknown population mean are likely to be different from each other. Although the focus is on detecting difference between several population of process means, the primary parameter used in this test based on a comparison of variance. So we will use the F test to compare the between means. So compare the variance, and we will use the variance to compare between means from different group. Okay, so again, if we have the group, let's like what we introduced before, so certain group, each will have different mean, and it can be either same number of population or different number of population. Okay, so the number of sample or population here might be the same or different. Okay, so in order to solve ANOVA problem, the same procedure as in chapter 5 will be used. Basically, we have 5 procedure steps for an ANOVA test. Okay, first step, as usual, we need to state the hypothesis statement, H0 and H1, and then determine the test statistic to be used. So on our ANOVA, we will use the F test, okay, for ANOVA, and then we establish the test criteria for by determining the critical value point and rejection region based on the significant level alpha. So we will find what we must know what is alpha, and then make a decision to reject or fail to reject H naught. So if the F test lies in the rejection region, then we reject H naught. Okay, where F test is equal to ms TR, mean squared treatment, and mean squared MSE, which is mean squared error. So draw a conclusion to reject or to accept the claim. So one-way ANOVA. So by the end of this topic, you should be able to determine if there is significant difference between more than two population means when sample size equal or unequal using one-way ANOVA. So one-way ANOVA only involve one factor. In order to use ANOVA test, there are three assumptions for ANOVA that we must follow. First, the population under study follow normally distributed. So, which is population for each group must be in normal distribution. Next, the samples are drawn randomly, and each sample is independent of the other samples. And then thirdly, all the population from each of the sample value are obtained have the same unknown population variance, that is for k number of population. So we can all the population must have same unknown population variance, okay, for k number of population. So let's say this is one-way ANOVA table. So Xij refer to the J observation from the ith treatment. I dot Xi dot is the total of observation that ith treatment. Okay, meaning that the total of the first row will be X1 dot. The second row will be X2 dot, and so on. Okay, and then X dot J is the total of all treatment from the jth observation. Okay, so the total of the first column is the first J equal to 1, so X dot 1, and the total of the all treatment in the second column is the X dot 2, which is J equal to 2. X dot dot is the total of all observation. Again, this is the total observation for row, and also actually the total observation for column. Xkn is the nth observation from the kth treatment. Reminder, the roles of I and J can be interchanged. So since ANOVA is a test of comparing the difference for more than two populations, means a model can be built to represent the data interval 7.1 as follows. Okay, summation of Xij equal to mu plus alpha I plus sigma ij, where I is 1 to k and j equal to 1 to n. So xij is the observed from the ith treatment, mu is the overall mean, alpha I is the ith treatment effect, xij is the random error, and k is the number of population treatment. So n1 is sample size for ith population. Okay, let's look at the formula. The ANOVA test is based on comparison of two independent estimates, which is sum square treatment and sum square error for a common population variance. So the estimate that are composed of total variability of data is sum square of total. So this is sum square total equals to sum square of treatment plus sum square of error. So the formula is sum squared treatment is equal to summation for xij squared minus x squared over n. Sum squared treatment is summation of xi dot square minus summation x dot square divide with n number of sample minus divide with n number of total number of data. Okay, so once you get the sum squared total and sum squared treatment, so you can get sum squared error by minus the difference between sum squared treatment with the sum squared total and sum squared error treatment, where n here refer to total number of data. So the same procedure in 7.2 apply for the ANOVA test. Thus, the null and alternative hypothesis should be stated as follow. Okay, H naught is always a mean equal to mean 2 equal to until how many group that mean that you have. Okay, if you have 3 mean, so meaning that H naught equal to mean 1 equal to mean 2 equal to mean 3. Okay, H1 is summation mean I not equal to mean J. So meaning that at least for H1, when we say like this statement, it means that at least one population mean is different, or there are different between the population mean, or not all population mean are equal, or there is a treatment effect between treatment I and treatment J. Okay, what it means that if we accept, we fail to reject H naught, we can say that the population means are equal. Okay, there is no variation among the group. But if we reject H naught, we can say that the mean between, if let's say we have 3 mean, okay, at least one of these or more than these are different. Maybe the difference is between mean 1 and mean 2, or maybe the difference is between mean 1 and mean 3, or the difference may be within this all the 3 mean 2 and mean 3, mean 1 and mean 2, and so on. So meaning that at least one population mean is different or more than that. Okay. Okay, note that I and J are the case treatment. The test statistic F test is computed by dividing the value of mean square of treatment, mean square of treatment, with the mean square of error, MSE. Meanwhile, these two values are calculated by dividing the value of sum square with its degree of freedom. The formula can be summarized as follows. So we usually put the answer for the one-way ANOVA in this table. One is treatment, source of variation from treatment, error, and total. Okay, so we find the sum square of treatment, and then find the sum square of total, and from here you can get your sum square of error by seeing the difference between sum square total minus sum square treatment. And then the degree of freedom is k minus 1, n minus k, and n minus 1. Okay, and then the mean square treatment and mean square error is equal to the sum square treatment divide with the degree of freedom for the mean square treatment. For mean square error is the sum squared of error divide with the degree of freedom for sum squared of error. From here, then we can get the F test, which is the mean square treatment divide with mean square error. So this is what we are looking for, F test. And then from F test, we compare with F table. Okay, which from the we can compare with the F table. So we can make a decision from this comparison. Okay, let's look at the example to make it easier for you to use the formula. Okay, example 2. Four different components of circuits are studied to compare the amount of available noise. The following data is obtained. So we have four group of circuit and the result of available noise. So the first circuit A, we have 1, 2, 3, 4, 5 data. Okay, so we have 5 data for A, 5 data for B, 5 data for C, and 5 data for D. So we have 4 group here. So that's whether the result of available noise is the same for all different types of circuit by using alpha 0.005. Okay, so we need to calculate all the value. So from the model above, we can see that K equal to 4. K refer to number of group. So we have 4 number of group. And then we have data n equal to 5. Thus, the above can be explained as this. So you have first group, second group, third group, and fourth group. Okay. So J equal to 1, 2, 3, 4, 5. And then you need to find the total for each group. 87, 350, 138, 399, and the overall total is 1019. Okay, next, state the null and alternative hypothesis. And we see that from this question, you need to test whether the result of available nulls is the same for all different type of circuit. Therefore, our claim will be at the H naught. Okay, mean A equal to mean B equal to mean C equal to mean D. So this is the claim, and since this is equal sign should be at the H naught. Okay, so H1 is the different. Mean I is different than mean J, where I is not equal to J. So meaning that mu A might be not the might be different than mu B, or mu A might be different than mu C or D. Cannot be mu A not equal mu A. No, since I should not equal to J. So we are finding the sum square treatment. So sum square treatment, you just look at the total of the each group. Okay, so 87. So 87 squared divide with 5. 5 refer to number of data that you have, and at that group 1, 2, 3, 4, 5. So 587 squared over 5. And then this one 350 squared over 5, and so on. 5 because we have 5 data here. Okay, so sum square of treatment. So you get all this minus with total. If you look back at the formula, the value of the row, total value of row divide with number of sample, number of data in that group, minus with total value, total number squared, divide with n, where n is actually the total number of data. Okay, so you know that from this question, the total number of the data is 5 times 4, which is 20. We have 5 data here, 5 data here, 5 data here, and 5 data here. Total everything, we have 20 data. So minus with the observation value is 1019 squared, divide with the total data 20. So you get 12633.75. So sum squared total is each observation you need to square everything, total up, and then minus with again the overall total squared divide with 20. Okay, so you have this data. You need to find the square, and everything until here. You find the square and then you total up everything, and then you will get the sum square total minus with 1019 squared divided with 20, and then you will get this. Once you get these two value, your sum squared error equal to sum squared total minus sum squared treatment equal to 3017.2. Then you can put in the ANOVA table. So sum squared treatment is 12633.75. And then sum squared error 3017. No, you need to fill up this first. Sum squared total is 15650.95, and then your error, sum squared of error is 3017.2. So what is your degree of freedom? Look back at the formula. Okay, so degree of freedom for this is the group minus 1. So since our group have 4, so 4 here is 4 group minus with 1. So we have our degree of freedom equal to 3. Okay, for here total degree of freedom for total. So the formula is n minus 1. So total data that you have is 20. So 20 minus 1 is 19. So actually 19 minus 3 is 16. Or in other way, n minus k. N minus k. So our n equal to 20. Our k equal to 4. So 20 minus 4 equal to 16. Or in other way is 19 minus with 3. You also will get 16. So that is the degree for of freedom for treatment and also error. And the result you also can find the degree of freedom for total. Next, you need to find mean squared. So mean squared treatment is just the sum squared divide with degree of freedom. Okay, so sum squared of treatment divide with degree of freedom for treatment. Okay, sum squared of error divide with some degree of freedom of error. So the result you can find the what we are looking for, which is F test. So you get 22.330 mean squared treatment divide with mean square of error. So you get 22.3320. So from the table, test statistic, so F alpha, so you need to F alpha, and then K minus 1, and N minus Okay. Okay, from table 7, F distribution, so we have several alpha. We have alpha 0.05 at this value, and then we also can find alpha equal to 0.01, alpha 0.025. Okay, so in our case, our alpha equal to 0.05, 0.005. Okay, and the degree of freedom, so degree of freedom is 3 and 16. So that is why we get the value of 6.30. So from the test table, test statistic, so we can compare that the F test is more than the F from the table, which is the test statistic. So the decision is reject H naught. The conclusion, we can conclude that the result of available noise is different among the population mean of 4 different types of circuit at alpha equal to 0.005. Okay, now let's look at the exercise. Consumer organization tested 3 different brands of bulb in order to determine if there is a difference in the lifetime in hours for each brand. The following information was collected when a random sample was taken at each brand. So we have 3 types of brand. Brand A, brand B, and brand C, and each of the brand has the same number of population ataupun number of data in the each group. Each group will have 1, 2, 3, 4, 5, 6 data. And now the question are, how many treatment and observation involved in the experiment? And then B, test the equality of lifetime of the bulb based on the above data. Describe the result. Use 1% level of significance. Okay. Answer for A, how many treatment and observation in the group in the experiment? So the treatment is equal to 3, the observation equal to 18. Okay, calculate like what we did before and you should get this answer. But the first step, you must know that you need to state the null and alternative hypothesis. Mean A equal to mean B equal to mean C. And then H1 statement is mean I is not equal to mean J, for I is not equal to J. And then you fill up this table to get the F test. Okay, so look, you should know how to get all this value. So since you get all the value, you get F test equal to F 3.449. Okay, from statistical table, for test statistic, we will find F alpha, which is K minus 1 and also N minus K, which is in this case, your alpha equal to 0.01, your K minus 1, 3 minus 1 is equal to 2, and N minus K is equal to 15. Okay, so this one should be 15. So you need to read from the table for alpha 0.01 with degree of freedom 2 and 15. So from the table, our alpha equal to 0.01. Our degree of freedom is equal to 2. Another degree of freedom is 15. So we must get 6.36. So we will get from the table 6.36. So what we can say, the F test equal to 3.449, which is less than 6.36, and the decision is failed to reject H naught. So the conclusion here is there are no difference among the type of brand used. Let's say you want to solve ANOVA by using Microsoft Excel. First, before you start, if you want to use any analysis in Microsoft Excel, you must add data analysis in the data. So these steps only required once. So you do it once and then you can use it for the next time. So if you already set the data analysis in your Microsoft Excel, you can skip this step. Okay, let's look at the Excel file. First, go to File and then click Option, and then you can see that Add-ins. You need to find Manage at the below part. Then choose Excel Add-ins and then click Go. So you can see here you need to tick the Analysis toolpack, and then you click OK. So the URD adds the analysis toolpack. Next step is to key in the data. Okay, first you can insert the data. Okay, so once you insert the data, go to click on the menu, find the data, and then at the end of the tab, you have a data analysis. Click on that. Choose ANOVA single factor. And then enter the range. Okay, so to enter the range, you click here and choose the range for the data, which is, you choose here to here. And then you can click this. Then your alpha, let's say alpha is 0.05, so you don't have to change. If your alpha is 0.01 or 0.1, 0.2, you just change your alpha at this part. Okay, now I want my alpha 0.05, and then you just can click OK. So your this is the table for your alpha, which is in the new sheet. So your table at sheet 1, your data in sheet 1 and your result will be in sheet 2. Okay, so from here this is called summary output for ANOVA. This is your F, you will get your F total for sum squared is 95.48746. Okay, and then you can get your compare your F value, which is this one. You need to compare your F value with the F critical to make a conclusion. Okay, which is obtained from the Excel. So once you have these two value, you can conclude your answer. So you can check this way in finding your answer for exercise 2 and also exercise 3. But now you try use Excel to get the answer. Okay, before this you calculate manually, but now you use Excel to get the F value and also the F critical, and then you can compare. Okay, good luck.